Once you can calculate the critical angle, then you know any angle greater than that will be what causes this effect called total internal reflection. Let me get your attention here to these two diagrams that I have up on this whiteboard. This is the condition for the critical angle. You have a ray of light that is coming from the incident surface, which back from the applet we'll recall was water. It now gets to the surface, and because it is at the critical angle, we see that it refracts 90 degrees and goes along the axis here between the two surfaces. Now, in this diagram, you'll notice that here's the critical angle again, as we had right here, and any angle that's greater than that, as you can see from this diagram, will now cause total internal reflection to occur. So this is a very key concept to be able to calculate this parameter, because then it gives you a range of other angles in which total internal reflection will occur. To determine the right formula for doing this, we're going to start with Snell's law, because Snell's law really is the law of refraction, and all the physics that we need for calculating that is built within this equation. I'm going to go ahead and slightly modify this equation to make it a little easier to talk to. Since we're talking about an incident medium of water up here, this is the index of refraction of the water. This is times the sine, and now I want to know specifically what it takes to get a critical angle between these two media up here. So this now becomes the critical angle, replaced from just a general angle of I in Snell's law. And this is now equal to the index of refraction of the refracted medium, which we know to be air. So this is just N of A, which is air. And that's multiplied by the sine of the refracted angle. Once again, since it's now at the critical angle, I know what the measure of that angle is. It's 90 degrees. So I'm going to put 90 degrees in here. And I know that the sine of 90 degrees is equal to 1. So now I have the equation that the index of refraction of water times the sine of the critical angle is equal to the index of refraction of the air. Simple algebra will say that then the sine of the critical angle is equal to the index of refraction of air divided by the index of refraction of water. And now what I've got to do is isolate that variable, which is the critical angle, so I can solve for it. And I now have that the critical angle is equal to the inverse sine of the index refraction of air divided by the index of refraction of water. So this now is our key equation. The critical angle is equal to the inverse sine, and the index of refraction of the air was 1.00. and the index of refraction of water was 1.333. You will find that the critical angle is 48.59 degrees.